Morning, underclassmen pre-calc from CCTI. Mr. Prashar here once again. Hope you had a very enjoyable Memorial weekend. The weather was spectacular. It was excellent. You could not have asked for better weather Saturday, Sunday, and yesterday, Monday. So I hope that you were able to get out and enjoy, and I hope that you all remembered our servicemen. I visit the cemeteries. It's a tradition I always do it with my family now. I still do it myself. I go to the cemeteries, visit all my deceased relatives, and especially honor those that were in the military. I had both of my grandfathers. They fought in World War II. I had great-grandparents that were in World War I. And I even have a family member, Justin Wilson. He was in the Civil War. And we actually have, my family actually has a glass marble from Justin that was passed down from generation to generation. So that's an interesting thing we have in our family. But I hope you did take time to remember the men and women that lost their lives in the military for our freedom that we have today. This video is exclusively for the underclassmen in pre-calc, especially those going on to calc next year. So last video I did was on trig identities, and this is going to be essentially the second part of trig identities, which play a huge role in calculus, even more so I think than the graphing aspect. So this stuff, again, this comes from section 6.1 in your textbook. Even though I didn't assign you anything, Khan Academy is taking care of this, but if you have your textbook, which you should, I hope you didn't throw it out. We have to get them back somehow anyway. 6.1 is where you want to go. And I'm going to show you some more things that we can do at trig. For example, problem number 37 from 6.1 says we have the following. We have secant of x plus tangent of x times secant of x minus tangent of x. So this kind of looks like something we do in algebra a lot. This is a classic multiplication thing. In fact, this would be like your classic FOIL, right? So we're going to go ahead and multiply like we normally do. We just got to watch trig. Now it kind of sucks in a way, because with trig, there's always the thing you got to watch out for identities that are hidden in the problem. And it's not always as smooth as the algebra. So let's go through it. So you're going to do secant x times secant x, which means you have secant squared x. Don't you hate when that happens? The guy even jumped. You have secant squared x. Then you have secant of x times negative tangent x. That's negative secant x tan x. And tangent of x times secant x is going to be another one. I'm just going to call it plus secant x tan x, just in the same order we have here. Even though, just like in algebra, xy is the same as yx, secant x tangent x is the same thing as tangent x secant x. And then tangent x times negative tangent x is minus tangent x squared. So we have that. Okay, and remember, with trig functions, we usually put the exponent between the abbreviation and the variable. We don't usually put it at the end. That's just a trig convention that we have. Notice, just like in ordinary algebra, the middle terms are identical, so we can get rid of them. So we're left with secant squared x minus tangent squared x. And you think you're done, but not quite. Because as of trig, there's always these hidden surprises, a lot. And we have to be aware that this could be an identity. One of the identities that we learned was that we have tangent squared x plus 1 is secant squared x. And if we rearrange this identity, I think you're going to see what we have over here. So if we move tangent over to the other side, perhaps, right, and call this 1 equals secant squared x minus a tangent x, tangent squared x, I think we'll see that this thing is what we have over here. And what that thing gives us is just 1. So this whole operation boils down to the number 1. So that's all we have left. So your final answer here is the number 1. That's what happens when you multiply this. And essentially, This is just like in algebra if you had x plus y times x minus y. You double the first terms, you double the last terms, and the middle terms cancel out. So that's how you do that. Okay, so that's that'd be number 37 from 6-1. Now let's do another one like this where we have to multiply. This time we're going to have number 38, 1 plus sine squared theta times 1 plus cotangent squared theta. And when you look at this right away, you may think to yourself, maybe we should rearrange this, use the identity. But this one isn't quite put as an identity. This one could be, right? But this one here, remember we have this idea that sine squared theta plus cosine squared theta is 1. But if we rearrange it, we're not going to be able to get it exactly as we want it there. One thing is always going to be minus when we move it left to right. So we have to keep this one as it is. But if we can use an identity to shrink this down, we should. So 1 plus cotangent squared, remember what the identity here is. If you have cotangent squared theta plus 1, that's equal to cosecant squared theta. And guess what? That's exactly what we got. So this guy right here is going to become cosecant squared theta, just like that. And now this makes the problem nicer because now we can just go ahead and multiply using plain old distribution. So what we have here is 1 times the cosecant squared, which is cosecant squared theta, and sine squared times cosecant squared, I'm just going to write that as plus, so let's write this a little bit better, we'll put plus, this is going to be sine squared theta times cosecant squared theta, just like that. Now, let's see what happens here with the sine squared cosecant squared. How can you rewrite cosecant squared in terms of sine squared? Well, by now you should know about your reciprocal property. So I'm going to write this as times 1 over sine squared theta. And you see why we did that? Because what happens is these guys will cancel out, and all you're left with is cosecant squared theta plus 1. Do we have an identity for that? Well, we're kind of close, but not quite. So this is the best it's going to be. If this was a minus 1, then we could write that as cotangent squared, but we don't have the minus 1. So this would be the final answer, cosecant squared theta plus 1. And again, what we did was we transformed this quantity on the right into this identity. We left this one go because we can't quite make it an exact identity, and we just did the multiplication. Okay? Alright, so let's look at another example. How about we have one like this? This is number 47. What if we have 1 minus sine squared theta times cotangent squared theta plus 1. So say we have this, okay? Now, again, we look at these and maybe we have an identity, right? So the 1 minus sine squared theta, we could actually rewrite that thing. Because again, if you remember, we have sine squared theta plus cosine squared theta is 1. So if you move the sine squared over here, you're going to get cosine squared. So let's try that. And cotangent squared theta plus 1, that is actually cosecant squared theta. So we can rewrite it that way as well. Now the thing is, if we go and multiply these together, there's really not much we can do here, because we can't make this in terms of cosines, so we're kind of stuck. So this is a good example of how sometimes jumping right into rewriting them in terms of identities does not work. So this was a bad idea, but we had to try it anyway. So let's go ahead and get rid of this, and let's look at the original problem. This is what makes Trig tricky, because there's no written rule that gets problems right on the first try. It's intuition, as I say, and the more problems you do, the better off you'll be. So let's do this one using just the classic multiplication. So 1 times cotangent squared theta is cotangent squared theta. 1 times 1 is 1. Negative sine squared times cotangent squared is negative sine squared cotangent squared. And negative sine squared times 1 is negative sine squared theta. So this is just using classic multiplication here, okay? Now, what we want to kind of do is ask, is there any like terms? Unfortunately, there is no like terms you could peel and put together there. So now our next goal is there anything we can do to try to cancel things? And we have perhaps an opportunity right here with this minus sine squared cotangent squared. Because cotangent squared could obviously be written as 1 over tangent squared, but cotangent squared could also be rewritten as cosecant squared over sine squared. And that will knock out this sine squared. So that's our next thing we're going to do. So we've got cotangent squared theta plus 1 minus sine squared theta times cosine squared theta over sine squared theta minus sine squared theta. And now, as I said, these cancel out. You're left with cotangent squared theta plus 1 minus a1 not a1, excuse me, this should be minus a cosine squared theta minus a sine squared theta. So it's cotangent squared theta plus 1 minus cosine squared theta minus sine squared theta. Okay? And now we want to keep going and see, is there anything that we could do here to change anything? Well, we have, let's see, we have a cotangent squared theta plus 1. We have a minus cosine squared theta minus sine squared theta. The cotangent squared theta, right, we could write this plus 1, we have cosecant squared theta minus cos squared theta minus sine squared theta. Is there anything else we could do here? Well, there's no more identities. The cosine squared sine squared would be good if we had a plus in between them, and a plus here, because we could write that as 1, but I don't think we're going to get anywhere there. Doesn't appear to be so. However, let's try to rearrange this and get both of these on the opposite side. So again, sine squared plus cosine squared is 1. If we move that over to the other side, right, what are we going to get? You're going to have 1 equals negative sine squared minus cosine squared. Do we have that? Yeah, we do, right here. So now we could call this cosecant squared plus 1, just like that, okay? And I think this is going to be the best thing we're going to be able to do here now, because if that was a minus 1, we could call that cotangent squared, but we can't. So cosecant squared theta plus 1. Okay, so this might be a good place to pause. Again, go back and do these problems. These are a little bit more complicated because of the fact that we're using all these different identities in order to solve I shouldn't say solve, but to simplify an expression. In the next set of examples, we're going to look at simplifying and factoring, because factoring does play a role. If you hate factoring now, just wait till the trig is mixed in, right? So let's look at a problem like this one, number 49. Now we're going to be talking about factoring. So in the book we have sine squared theta plus cotangent squared theta sine squared theta. So we're adding those two things together. What we want to do is factor. So all the factoring rules that you know still apply. We just have to apply it to trig. That's the only difference. What do they both have in common? They both have a sine squared. So let's pull out the sine squared. And what do we have left? That's just going to be a 1 plus a cotangent squared. And what is 1 plus cotangent squared? Well, that is cosecant squared by identity, right? 1 plus cotangent squared is cosecant squared. And now we have an opportunity to do something nice. We could write cosecant squared as 1 over sine squared. So we got sine squared times 1 over sine squared. And lo and behold, they cancel out. And just like that, you're left with just the number 1. So once again, we're using these properties, these identities, after the factoring to go ahead and shrink things down. So you have to be on your toes, and this happens in calc a lot, where we have to be able to kind of see these things in the works in problems to be able to simplify. Okay, so let's look at another example like this one. This will be number 50. In this one we have cotangent of x times cosecant squared x minus cotangent x. And again, the direction here is we want to factor. So if you want to factor this, you go after, what do we have in common? Well, they both have a cotangent, so we're going to factor out the cotangent. So you got cotangent x factors out, you're left with cosecant squared x minus a 1. And once again, hidden in the shadows is cosecant squared x minus 1. That is an identity. So what that identity is going to do is transform this into, do you know what it's going to be? Remember where it comes from? We have cotangent squared x plus 1 is cosecant squared x. So if you drag this one over here, it becomes minus. So it's going to be cotangent squared. So you got cotangent x times cotangent squared x. And there's not much we can do here other than multiply these two together. So remember, when you have like bases, which we have, they're both cotangent of x's, you add the exponents. So your answer is going to be cotangent cubed of x. That's it. So your final answer is cotangent cubed. Now, my last three examples are probably the most complicated of the factoring because we really have to use the identities, and these are 3-term or 4-term trig functions. So they're like polynomials, but with trig functions instead. So these are the ones that's a little more complicated. So this is actually number 53. And 53 says we have secant squared x plus 6 times tangent of x plus 4. So when you look at this thing, this is a little bit more daunting. You have 3 terms, and just like in algebra, we want to get these in sets of 2 parentheses, right? It makes it tricky because if you go by what we know from algebra, we'd be saying, okay, we'd have to have secant x and secant x, and then like a 2 and a 2 or a 4 and a 1 in the parentheses, right? But look what your middle term is. It's tangent. This is secant, so there's no way in hell you're going to be able to get tangent by having secant and secant here. So here's what your trick is. Whenever you have 3 terms in factoring, you go to this middle term. The middle term is tangent. So what we got to do is we got to get this secant written in terms of tangent. And we can do that because we have an identity. The identity says tangent squared x plus 1 is secant squared x. So everywhere you see a secant squared x, we're going to write tangent squared x plus 1. So this has nothing to do with factoring, it's just the identity rewrite problem. So I'm going to write now tangent squared x plus 1 plus 6 times the tangent of x plus 4. And again, before I even factor, I'm going to do any kind of simplification I could. We could put together the 1 and the 4. So I'm going to have tangent squared x plus 6 tangent of x plus 5. I'm going to put the 5 at the end. Just like in any algebra problem we want to factor, we keep just the constant at the end. Now you're in good shape because this is tangent and tangent, so we can split up as tangent apiece. So in your 2 parentheses you've got tangent of x and tangent of x. They're both pluses. Things that multiply to 5 but add to 6, the only choice you have is 5 and 1. So your answer is tangent of x plus 5 times tangent of x plus 1. And there you have it. So factoring is a little more crazy here with trig. You got to put your seatbelt on. First step is to look at this middle term. Rewrite the trig function as the middle term when you have 3 terms, and then proceed to factor. Okay? I think we're going to want to look at another example of this. So you might want to pause this and try this one again, or wait until I do the next one and then pause. Okay, this is going to be number 54. And 54 says cotangent squared x minus 4 cosecant x plus 5. And we want to factor this thing, right? So once again, you have a cotangent versus a cosecant. You go after that middle term. The middle term is cosecant, so that means we got to try to get this cotangent to become a cosecant. And again, how do we do that? By knowing your identities. Again, not to beat a dead horse, but the identities are crucial for trig. So what do we have as an identity? Well, we have cotangent squared x plus 1 is cosecant squared x. So what we're going to do here is, this is cotangent squared x. That means we got cotangent squared x equals cosecant squared x minus 1. So everywhere you see the cotangent squared x, we're going to substitute in cosecant squared x minus 1. All we did was alter the identity over there to get it to work. This is cosecant squared x minus 1 minus 4 cosecant of x plus 5. And once again, like in that last problem, combine your like terms. You got a minus 1 and a plus 5. So that's going to be cosecant squared x minus 4 cosecant x. And this will give you a plus 4. So again, all we did was we rewrite it using identities. And now we could go ahead and factor. So we're going to have a cosecant x and a cosecant x. These both have to be minuses. Things that multiply to 4, but add or subtract to combine to give you a -4 has to be 2 and 2. So it's cosecant x minus 2 times cosecant x minus 2, or we could write it as cosecant x minus 2 to the second power. You have to have some guts to do these types of factoring problems. They're not as laid back as the usual ones from algebra. In algebra, you remember we had difference of two squares, perfect square trinomial, difference of two cubes, sum of two cubes. That stuff spills over in the trig, as you're going to see in my last example here, that you have to be on the lookout for. Okay, and what I'm going to do first is I'll do an algebra problem just so you can see it. For example, if I gave you x squared plus, let's say, 8x plus 16, this is what we call a perfect square trinomial. Because the first term is a perfect square, and the last term is a perfect square. So we could write this as the sum of the squares squared, x plus 4 quantity squared. The same idea happens here in trig. Okay? So let me write it underneath here so you can see the parallel. So here's a problem. We have 9 sine squared t plus 42 cos t sine t plus 49 cos squared t. Right? This is in disguise a perfect square trinomial, essentially, because 9 has a perfect square of 3, 49 has a perfect square of 7, sine squared has a perfect square of sine, cosine squared has a perfect square of cosine. So watch how easy we can make this. This is going to be 3 sine t and 3 sine t. They're both pluses because everything is a plus. 49 square is 7, so that's 7 and 7. And they both need a cosine. So 3 sine t plus 7 cos t plus 3 sine t plus 7 cos t. If you do the math and multiply them out, you'll see that you do indeed get this back. You know, so I encourage you to try that just to verify. Right, so we covered an awful lot today. We really did. And again, this is big help for the underclassmen, especially those going into calc next year. You gotta know how to do this. We review a little bit of this. You will be reviewing over the summer, and coming up later in the week, I'll be telling you about your summer assignment that you have to do if you are going to be in AP Calc next year. And when we start Calc next year, we'll spend a little bit of time with this, but not too much time. So make sure you get acquainted to it as much as you could. Until then, if you have any questions, please feel free to call, email me. I'll help you any way I could. And again, hope everybody is doing well. I do miss all of you. I miss being in the classroom. This is not, to me, this is not teaching. But we got to do what we got to do. And I hope that I'll be able to see everybody sooner than later. Until then, enjoy the day. Make sure you get out. And I hope that you enjoy it. Take care.